I'm going to talk about one of my theories that I've discovered, but I haven't been able to actually test this because, frankly, I don't know how to program. I've been trying to teach myself, but I just haven't had the time or resources to do it properly, to teach myself properly. But I know exactly what I have to do for it, and the only thing that's stopping me from writing a research paper on this, well, there's two things actually. First of all, I don't have any way of getting peer review, but I did find out recently about ArcSiv. Well, I knew about ArcSiv a long time ago, it just didn't occur to me. I didn't remember about it until very recently. So I'm going to, but I still, even then, I can't post anything to ArcSiv until I actually render the thing that's coming from my theory. But I will eventually get around to doing this. I first thought of this when I was lying down on the bed sometime about a year ago, probably March around, and I'd noticed that any Fibonacci number, well, if you take the Fibonacci sequence and you take any two starter seeds and you plug them into the Fibonacci iterator, and then you take the limit as n approaches infinity and the limit as two consecutive terms, the ratio between two consecutive terms will always approach phi, the golden ratio. This is known. This has been known for a fairly long time. But what I thought is, why don't we apply this to fractals? And what I said is that we have the Euclidean plane, we have a point x comma y, and we define x to be f sub 0 and y to be f sub 1, and this order does matter. Then we use these starter seeds as starter seeds to the Fibonacci sequence iterator, where f sub n plus 1 equals f sub n plus f sub n minus 1, or alternatively f sub n equals f sub n minus 1 plus f sub n minus 2. And what we do is that because these approach phi at different rates, we use a process very similar to what's used to color the Mandelbrot set, or really any other fractal of the sort, except there really aren't any points that are in the set. There could be, but I'd have to see the render to be for sure. So what we do is that we have a gradient that goes from 0 to n, where n is a specified number of iterations, and this gradient, the 0 to n, is just an injection onto a color gradient, where let's say that we have, I hate to use the hexadecimal term because it's different and when you actually use the hexadecimal, but f over n would be one step, but it's different in when it actually comes to getting the gradient, but you get my drift. So we're basically assigning a color value to the iteration depth, where 0 would represent the leftmost side of the gradient and n would represent the rightmost side of the gradient. What does this mean? Well, 0 would mean that the ratio between the starter seeds themselves is exactly within a certain percentage of phi. or it's phi itself, as would be the case with starter seeds 1, phi, and any combination of the sort. One might think that, oh, wouldn't there be an infinite number of lines with slope phi, or a multiple of phi, that the ratio gets to, is 0? And yes, there might be, but one would think that's true of the Mandelbrot set too, but that's not necessarily true, and we all know how complex the Mandelbrot set is. So what we do is, now that we have this iterator, now that we have this process, this gradient process, we see how we define a percentage, the ratio after n iterations is from phi, and we need that's a percentage error, a relative error, and we're going to see how many iterations it takes to get within that defined value, up to a certain specified number of iterations, n. If it hasn't yet gotten to that point yet, gotten to the ratio yet, or has just gotten there, it would be the color that n is assigned. Else, the iterations below it would be assigned values on the gradient depending on the iterations. Of course, this has a computable limit of about 1.6 million iterations, because that's how many colors there are on displayable on the screen. But at the same time, what we could do is that we could just repeat that over, even though it wouldn't look nice and it wouldn't look proper. It could be a bit confusing. The process is still kind of used in the Mandelbrot set. So now we have the process to say, okay, this point after n iterations is this color. Obviously, now we just assign this color value to that point, and we let n approach infinity. We really can't let n approach infinity, because we want n to be sufficiently large enough so that it can cover a large portion of the plane. The only problem here is that the change in closer values, well, not necessarily closer, but change in similar values would not appear as pronounced as the lower iterations, but it wouldn't be as accurate. So this is a double-edged sword. But the point is that we can map this to the Euclidean plane to get an idea of the rates towards phi. And this can be used for other processes too. Not just an approach to phi. If you take, for instance, if you add the last two terms to the current term and keep doing that, the ratio between two consecutive terms then is actually more about 1.83. So, and this will work for any number. This can be extended into the complex plane, the hypercomplex plane, whatever it is. I mean, if I knew how to use quaternions, I would. But I'm kind of in only AP calculus, so if the fact that I'm doing this enough is, at my age, is okay. So sooner or later I will get around to teaching myself quaternions, and I will apply that to this process and extend this into the hypercomplex plane. And this can be the hypercomplex plane, but you'd have to use like cutouts of the thing. We can't use three-dimensional points unless you're going to use the three-dimensional process. Just, you can't use it for the Fibonacci iterator. You can use it for other processes. But I personally found it extremely fascinating that with enough iterations that we can create this map, which I call the Fractal Phi map. And so once I actually get around to writing a thesis paper for that, after I, learn the program or have someone help me program it, I will. And regardless of where I go, it's not MIT, at least not for next year. I'm still waiting on my Caltech application, which is now my next goal, because they have the best cosmology program in the world by a very, very long. They're pretty good at math too. And I've talked to many Caltech students, and they said that I would fit in there Then it's the next choice would be Berkeley, then UF, University of Florida, then Georgia Tech. The only reason why I'm putting UF before Georgia Tech is because, one, it's in-state and it'll be cheaper for me. Two, they have the best lightning lab in the world, and I don't know if you've subscribed to me for that long, but if you remember, my username used to be Awesome Lightning, and if you look at my older videos, there is a ton of lightning videos. And I recently was able to activate the video my very first video that I tried to upload, but I couldn't because it was too long at the time, but I reactivated that very recently. So you can see my 12-year-old self talk about lightning as though I was one of the students working at UF researching lightning. Always obsessed with it. And I actually got to talk to them, and they're pretty cool. Dr. Moore and stuff. But yeah, UF isn't a bad school. It's just that, one, I don't want to be around students from my school, and two, just because my grades are low doesn't mean that I'm not good enough. Because it's all about placement. If I find me the right place, I will go far, and nothing's going to stop me. Then my very, very last resort is UCF. And even though I'm kind of wearing their colors, it's purely coincidental. But UCF is just no thank you. It's UF was itself my backup school, but this is the complete last resort. But yes, I'm going to eventually write a paper on this, and hopefully one day I can solve the Millennium Rise problems. It's a pretty big dream of mine, and I'm just going to study something. I will own the field of science and mathematics for my generation. Just as Carl Sagan and Neil deGrasse Tyson was in their respective ages, is Neil deGrasse Tyson. And I'll be not only opening young minds to the beauty of the cosmos, and also open them to mathematics, because no one really does that, and I want people to be open to that, and people have opened to the cosmos, can open them up to math too. Just give me a chance. So, yep.